Welcome to Chapter 9, The Arithmetic of Chemistry. So we'll start this chapter with a quick demo about dilution and pollution. That the common saying, whether this is true or safe, is the simplest solution to pollution is dilution. That at a certain point, when can you tell it's there? Okay, we're gonna use some water and some food coloring to understand the concept of dilution and pollution. So the demo in the book suggests you use salt water. However, that's kind of hard to show up on camera unless you want me to be really mugging it and give you some sight gag as I drink salt water. Instead, I'm gonna mix in some food coloring. It's 50 mils of water. I'm gonna add 2 drops of green food coloring and stir that in. And then we're gonna dilute that 10 mils into 50 a couple times. So we have a nice deep solution. Very well dyed green. So we're gonna pour 10 mils of that into clean water. Mix that in. You can already tell it's significantly lighter than our original starting material. Moving on to number 2. It's still faintly green, not much. Third dilution. I'm not sure you could even really tell this was green except for a little bit at the top. A little bit at the top. Where it kind of catches the light just right. On that, it's almost impossible to tell. Compare it maybe a little bit. Another. Not sure you can tell at all. Not sure you can tell at all that maybe. No. And if I keep going, we'll go ahead and keep going since we're on a roll. And the last one. Now, all of these have some molecules of green dye in them. But see, clearly, some of these don't have enough green dye for us to physically see it with our naked eye. What point would you say there's no longer green dye? What point would you say this is no longer polluted? Would you be willing to drink this one if I handed it to you and didn't tell you it was green dye? Would you be willing to drink this one? Maybe that guy? It's so hard to tell, especially when some of these guys are not so readily observable. That's the same thing you would see. As you diluted the salt would have been less and less potent until you might not even be able to taste it at all. But the first one would be dangerously salty, like drinking salt water. So that is a quick demo about dilution. Now, when buying things, we often buy in certain quantities. If you're buying socks, you're going to buy in pairs, whether it's 6 socks or just 1 pair of socks. You're not going to just get one. When you're buying drinks like beer or soda, you might get a 6-pack, you might get a 12-pack, you get a 24-pack. Very rarely, you're just going to buy one. you're going to buy paper, you're going to buy it by the ream. You're going to buy a bundle. You're not going to buy just one piece of paper. It's going to be silly. Well, the same thing's true with atoms. In atoms, we want to use a quantity that makes sense for us. Except with atoms, it has to be on a completely different scales. If we try to count out even 100, it's too small for us to. Now, there's more atoms of carbon in a lump of charcoal than there are stars in the sky. And that's saying a lot. There's approximately 70 billion trillion stars, or by current estimate, in our galaxy, which is 7 times 10 to the 22nd. Now, to manage this, we'll need some new words and be able to count particles, and we'll need some arithmetic. So just to make sure we're on the same page, I'm going to take a few mathematical asides. We're going to go into a few things, get some key concepts in before we start on the actual math. Okay, thinking about like how we think of numbers, Roman numerals, all nifty and great ways of numbering our Super Bowls and movies, are not really practical. They're kind of hard. You look at the simple numbers, you got I is 1, V 5, X 10, L 50, C 100, D 500, M 1000. And you use the previous number up until you get to one before the next. So you'd I, V, and then you go VI all the way till you get to IX. And then when you go to 40, you'd be XL. You go to from 50 to 100, you would have XC, I think. But you keep going. And so on short numbers, it's not too bad, but in long numbers, it can be a little tedious. Like when I'm making this video, 2021, you'd have M, X, X, I. So 2000s, there's 0 and the hundreds, and 21. If we want, but which by itself doesn't look too bad. But if we're going like, say, a different year, like say the last year the Bears won the Super Bowl, 1986, that would have to be what? Like, be MCM LXXXVI. And it starts to get really complicated. So that's why we have adopted Arabic numerals, that they run simply 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are Arabic numerals. And we can append any number to change a decimal place by multiplying it by adding a 0. So to get to 10, we add a 0 to the 1. So, and we can then deal with that. We can scale up by just adding more zeros. These are much easier. So if I want to say 1986, I just have 4 numbers instead of 9 numbers. So we can make it simplify a lot of things. Now, however, Arabic numerals can still be cumbersome if the number is big enough. Thus, we have to introduce exponential notation. Exponential notation is a number raised to a power. So like 5 squared, 5 raised to the power of 2 would be 5 times 5, which is 25. So it's a number times a number n times. If I wanted 4 cubed is of course 4 times 4 times 4, which is going to be 64. We can do all these numbers by itself. We're going to take the base, raise it to the power of an exponent. Now, with that in mind, we're going to do our exponents with a base 10 to help us turn this into what's called scientific notation, something I will use quite often because of how it helps us with our math. Now, with a base 10, we can, the exponent will tell us how many places to move the decimal. So if I have 2 times 10 to the third, with a positive exponent, I move the decimal to the right. So I'll say 2, and I move the decimal 1, 2, 3 to the right. So that would be saying 2000. On the alternative, if I have 1.8 and I have a negative exponent, I would move the decimal to the left. So this would be equal to, I'll move the decimal 1.8, we moved it 1, 2, 3, let's see, 1, 2, 3, 4. We moved it 4 to the left. So we've essentially turned this number from this number. And what the book doesn't tell you is that if the exponent is to the 0th power, we don't move it at all, which is an often forgotten term. So 5.1 times 10 to the 0 is just equal 5.1. It's left off because it's an identity property of exponents. Any number raised to 0 is equal to 1, and any number times 1 is itself. And one final thing to note that will help with some math, we can, when multiplying two numbers with exponents, we can add the exponents if the bases are the same. So if I had 2 squared times 2 cubed, the sum, the answer would be 2 to the 5th, because 2 plus 3 is 5. And so we're going to do 2 to the 5th power. So oftentimes this is going to be used if I have 10 to the negative 3rd times 10 to the 8th. What is 8 minus 3, or 8 plus negative 3? That's going to be 10 to the positive 5th because of the rule of exponents. So these exponents will be used very often, and we need to get used to seeing them. So we're going to take a quick aside and look at the metric system and where that came from. Well, it started in 1789 with the French Revolution against Louis XVI, XVI, in case you remember the Roman numerals. Well, when the French removed Louis, they also kind of revolted against the status quo and the current scientific establishment, because units were the key things of measuring everything. If you wanted to pay for something, you would use the king's money, which would be weighed out in so many ounces of gold or something, which all the units were based on arbitrary figures, something the king decided on, and you would have to measure it against what the king felt. Sometimes these were very hard to reproduce. Like if you're like, oh, the king's foot is this, is our measurement of a foot. Well, you have to copy that 1 foot in order to match it. And so you don't really have a good scale to measure against. Just for example, the English yard, which was established by Edward III in 1353, it's a weird concept. It's 3 feet. We don't really use the yard for anything else other than occasionally we turn feet to yards. We use it in a football field. But you gotta remember, so 3 feet to a yard, 12 inches to a foot, 5,280 feet to a mile. We don't even turn yards to miles, really. We know the feet to miles. All those are strange numbers. They don't really fit a logical comparison. And even before that, there's extra problem if you're trading with another country, because each country has its own systems of measurement. So if you're going from France to England, a gram in France is not necessarily a gram in, well, grams didn't exist back then, but say an ounce or whatever. This much gold would be a different number of gold in England than it would in France because of how they measured it. So what we did is France had all of its standards that were by royal decree. And so it didn't really make sense to keep the king's numbers when you're already throughout the king. So we would replace those with what we call the metric system, which is Greek from metron, which means to measure. 1791, the French government has 12 scientists come up with the new standards. And they say, let's try to, those scientists want to measure it on something universal that everyone can understand. So they used Earth as our standard. They say 1 meter is approximately 1/10,000,000th of the distance between the equator to the pole, whether it's North Pole or South Pole. So it's 1 meter is 10 to the -7th. That distance between the Earth, the equator to the pole. Now, well, don't ask me how they measured that. That's what they got. Now, the metric system, one of its big advantages is it uses prefixes to represent orders of 10. For example, so starting with meter as a basic, if I wanted to have 1,000 meters, we have a kilometer, which is 1,000 meters. Kilo comes from the Greek kilioi, which literally means 1,000. The Greek kilioi, which is 1,000. So a kilometer is equal, 1 kilometer is equal to 1,000 meters. Now, when it came to area, we could measure area as squares and cubes of length. So we can say that the area of a room is so many meters, say 1,000 meters squared, because you had 100 meters by 10 meters. So, or say, and then space being meter cubed. Now, one of the common units we'll use is centimeter cubed. 1 centimeter cubed. A centimeter by a centimeter by a centimeter, a centimeter. There is 100 centimeters in 1 meter. So so a centimeter cubed. Often referred to in nursing and doctor work in medical field as a cc, cubic centimeter. But so while we measure volume as meter cubed, we often find it more useful to give this as a liter, which comes from the French litron. But basically, 1 liter is equal to, or at least was equal to, 10 centimeters by 10 centimeters by 10 centimeters. So essentially, 1,000 centimeters cubed is equal to 1 liter, litron. And the next, we use the mass. How do we determine a mass? Well, the mass, we came up the unit of gram. The gram was literally based on water and our length. 1 gram was defined as the weight of 1 centimeter cubed of water at its maximum density point, which was 4 degrees C. So, and the gram comes from, whether Latin or Greek, it's from gramma, which means small weight. Now, the actual standard we use is 1 kilogram, which is the weight of 1 liter, because kilogram is much more useful. But so in December 10th, 1799, the French Legislature Assembly officially adopted these standards. Now, there's kind of some silly stories involved with this, though. Despite these good intentions on the meter, you actually still have to have a physical standard. You can't just go up and measure 1 10 millionth of the Earth whenever you want to measure a distance. We need a simple standard we can measure all of our rulers against, so we can know whether this ruler is printed accurately. So they made cut a platinum bar as best as they could to be exactly a meter in length. And this was used during most of the 19th century. Now, of course, over time it becomes worn and nicked and damaged. And so they needed a replacement. And plus, on top of that, the old meter is actually slightly inaccurate. So our meter definition was temporarily replaced by an arbitrary standard, which is with the distance between two lines marked on a bar that was originally based on the original length of the original bar. But once again, we're supposed to be referencing something that's not going to change, like the distance on the Earth, not a random bar that we chose. But now we're back on track with our discrete constants that scientists have measured something that's not going to change, which is, while it's kind of an arbitrary distance, it's the distance light travels in 299,792,458 of a second. Basically, they measured a meter against the speed of light, which is something that could hypothetically be measured, and that could be once again, we're back to a definite standard. Now, the mass of a platinum cylinder, which we use to measure 1 kilogram to compare against 1,000 centimeters cubed, was also kind of a little inaccurate. With now, when we originally measured it, we couldn't measure it as accurately to the correct number of places. So, but we now know that the measurement we had was 1 kilogram was actually had a volume of 1,000.028 centimeters cubed, slightly higher than we actually thought because of what we were using. So, and we found it easier to change the definition of the liter than it is to change the definition of a kilogram. So we've now defined a liter to be a volume of 1 kilogram of water rather than a kilogram to be 1 liter of water. So now, technically, this is not the case. 1 centimeter cubed does not equal 1 milliliter. Usually we say that these are equal, but it's not actually true. Now, is it true enough for all of our daily lives? Yes. Yes, it's true enough. We can say that 1 milliliter is actually equal to 1.0000093 repeating centimeters cubed in 1 milliliter. Are we going to notice that? No. But for the people who are the anal retentive accuracy people, yes, they will notice it. So not enough to change this, but enough for these people to lose some sleep over, as the book says. But the U.S. would officially adopt the metric system in July 28th, 1866. But of course, English system has been used for such a long period of time that it never really went away. So they're both in common usage, but scientists really like the metric system because it's all base 10. Now, a few common metric units, like, for example, a meter, starting there. We go a kilometer. There's 10 to the third meters. We can have a mega meter, which is capital M, 10 to the 6th meters. We can have a gigameter, like a gigabyte, a megabyte, 10 to the 9th meters. We could even have a terameter, 10 to the 12th meters. Going down, millimeter, which is 10 to the negative third meters. We often will have centimeters. And even though we don't really use these guys, they're there. We can have decimeters, which is 10 to the negative first meters. We can have micrometers, which is 10 to the negative 6th meters. And we'll see nanometers, 10 to the negative 9th. And of course, we could also have picometers, 10 to the negative 12th. And we could actually go far larger and smaller. However, we will not really see much larger and smaller in our everyday lives. So we won't worry about those. We probably won't even see giga and tera, maybe not even mega, but just know they are there. And you can do the same with liters. Start with liters, kiloliters, megaliters, gigaliters, milliliters, centiliters, microliters. They're all there. They're all the same and they work exactly the same. And the last mathematical side we will look at is of unit cancellation. Complex equations can be solved through unit cancellation. Now, we must set up a ratio of units with the numerator and denominator. So we can cancel out units if there's a match on the opposite side. So let's take an example. I work at for $12.50 an hour. So my ratio is money per hour. And I work on average 40 hours per week. And Social Security tax is 6.2 cents per dollar I earn. 6.2% per cents, so 6% per dollar, essentially. How much am I paying to Social Security in 1 week? So I'm going to set that up. So my first ratio, $12.5 an hour. Set 40 hours in 1 week. And set up 6.2 cents for every $1 I earn. So the dollars cancel, dollar sign cancels out. My hours cancel out, and my units are left with pennies per week. So everything on top gets multiplied. Everything on bottom gets divided. So I'd say 12.5 times 40 times 6.2. I'm paying the government 3,100 cents, which is, if I turn this back into dollars, I'm giving the government $31 per week out of my paycheck to go to Social Security. Let's look at another one. Say the gas costs $2.88 per gallon at the gas station, which, depending on where you're at, that might be a little low, it might be a little bit cheap. Say my car gets something like 25 miles to the gallon. And say I want to drive to Nashville, which is 128 miles to Nashville. So the question here is, how much money do I have to spend in gas to get to Nashville? We want money to go to Nashville. So we have our 288 up 3.8 per gallon. Now here's where I switch this around. I have 25 miles in 1 gallon. And I have 128 miles to go to Nashville. So gallon, miles. And so it would have the cost to Nashville. So I'd say 288 times 128 divided by 25. So it would cost me something like $14.75 in gas to drive to Nashville. $14.75 in gas. One more. Let's say a chicken lays something like 6 eggs a week. per chicken. 6 eggs a week per chicken. And I have 15 chickens on the farm. And I lay, and we're running the farm for 52 weeks a year. The question here is, how many eggs do we get on the farm in a year? So we're putting that, start with our 6 eggs per week per chicken. We have 15 chickens on the one farm. And we have something like 52 weeks in 1 year. So the weeks cancel here. My chickens cancel here. And we're going to have our units of eggs on the per this farm in a year. So 6 times 15 times 52 would have something like 4,680 eggs to sell on that farm. Now, all these are just examples of unit cancellation. We will do this more later. We'll do this more later. But for now, I'm just showing you this is how we'd go about doing this. Now, let's get back to the actual chemistry of this. Well, before we can actually measure atoms, we need to recall what it means to be a balanced chemical equation. Let's look at some simple guys. Like, let's do ethanol, C2H6O. The combustion of ethanol in the presence of oxygen will produce the byproduct of CO2 and H2O. To balance this, we need to make sure all the carbons, all the hydrogens, and all the oxygens on both sides are the same. These numbers will change as we go. 6 and right now 3. 1, 2. Right now, by itself, you'd say, oh, the oxygens are balanced. But remember, we do the oxygens last, and everything has to be balanced. So first things first, I'm going to start with the carbon. I always leave the oxygen for last. So carbon. If I doubles that, and changes that 4. So that's now 5 on the oxygens. Hydrogen, we got 3. Well, we got 6 there. We got 2 there. So we're going to need a 3 here. Change it 3 to 3, 4. That goes to 7. Now, if I change a coefficient here, that's going to change these 2 guys. So instead, I want to change the coefficient here. So if that's 7 and I got 1 from here, I need 6 from this guy. So that means I'm going to have a 3 there. Now I'll get that to a 7. Now we're balanced. 2 carbons, 2 carbons, 6 hydrogens, 6 hydrogens, 7 oxygens, 7 oxygens. The law of conservation of matter is obeyed. What does this mean now? It means for every ethanol molecule that burns, we need 3 molecules of oxygen to burn with it. For every 1 ethanol molecule that burns, we produce 2 molecules of CO2. And for every molecule of ethanol that burns, we'll produce 3 molecules of H2O. That when we look at this, we'll need this to help us understand a molecule ratio. Well, the book talks about a simpler reaction. We'll look at that one as well. Carbon plus oxygen goes to CO2. Well, how much oxygen would you need to burn 36 grams of carbon? If I have 36 grams of carbon, how much oxygen would you need? Well, carbon has the weight of 12 AMU, pulling directly from the periodic table. Technically, it's like 12.01, but we're going to use the simplest number right now. Looking at oxygen. Oxygen by itself is 16, but because it's a diatomic, oxygen weighs 32 AMU. So the ratio is that for every 12 AMU of carbon, we need 32 AMU of oxygen. So so we can set up a ratio. The grams of O2 over the 36 grams of carbon is equal to 12 AMU of carbon over 32 AMU of O2. Looking at that ratio, cross multiplying, you'll get that 36 times 32 divided by 12 give you that you would need 96 grams of oxygen to fully burn 36 grams of charcoal. We can use the ratio of AMU to AMU to get grams. Now, as easy as it is to have ratios between numbers, it's actually nicer to have a specific number of particles that we can measure. And that's where we get our first term for the chapter, which is a mole. A mole is the number of atoms of carbon-12 in exactly 12 grams of carbon-12. As you saw in our metric unit, we like to have something practical that everyone can measure against, so we don't have an arbitrary number. So we designed this perfectly for carbon-12. Now, in practice, a mole of a substance is the number of chemical particles contained in its atomic, molecular, or ionic weight, expressed in grams. Basically, this will allow us to turn a term in AMU per element into a gram per mole. So when we say carbon-12 weighs exactly 12 AMU, we're saying 1 mole of carbon-12 weighs exactly 12 grams. If I say oxygen diatomic weighs 32 AMU per compound, then it would weigh 32 grams per mole of oxygen. And one of the big concepts that we need to recognize is 1 mole of element A is going to be equal to 1 mole of element B. So 1 mole of oxygen will equal 1 mole of carbon. It's a counting number. Like if I said 12 dozen cans of soda would be the same as 12 dozen eggs. That it's the same number, even though they're completely different subjects. Which gets us to Avogadro's number. Specifically, it's 6.02 times 10 to the 23rd, which is the experimentally determined number of chemical particles within a mole. It's named after the Italian physicist Amedeo Avogadro, who was born in the year of our Declaration of Independence, and his pioneering work led to how we now count atoms. A mole is a really big number. That's 6.02 times 10 to the 23rd. To help conceptualize this, imagine stacks of pennies, 400 pennies high. So a stack of 50 is one of those rolls, like 8 stacks of them high. And you place them in the space around the earth. A mole worth of pennies would fill in all the space between the Earth and the moon's orbit. If you read XKCD or read his book, What If, he explored the question of what would a mole of furry critter moles be? What would a mole of moles be? Well, if you actually gathered a mole of moles, the mass of that would weigh just over half the mass of the moon. If you placed them on Earth, it would cover the Earth 80 kilometers deep, as the image shows, smothering everything. That this whole space right here is all moles. It's moles all the way down. There's Mount Everest, 80 kilometers of moles. That's how many moles a mole of moles would be. It's a little silly. hopefully you've heard the riddle, what weighs more, a ton of feathers or a ton of bricks? Kind of a lark, because really they weigh the same. A ton is still a ton regardless of the what it's made of. So the book asks you which has more atoms, 1 mole of lead or 1 mole of gold. But you can even do 1 mole of helium. 1 mole of helium. Which has more atoms? Well, the answer is neither. 1 mole is still 1 mole, regardless of which one, because that is just a counting number. If you said a dozen chickens versus a dozen eggs, how many, which one's more? Well, a dozen is still a dozen, regardless of whether you talk about big chickens or little eggs. So big lead versus little helium, they're both the same amount. Now, which weighs more? Well, clearly the lead, because lead has a molar mass of 207 AMU per element. So it would be equivalent to 207 grams per mole, while helium has a ratio of 4 grams per mole. So which has more atoms? Neither. Which weighs more? Clearly the lead's going to weigh 207 grams, while the helium's only going to weigh 4 grams. Now, which one has more atoms? 1 gram of lithium or 1 gram of iron? So this one we have to think. They both weigh the same because it's the same weight. But which one has more atoms? Well, lithium has a weight of close to, I'd like to say, 6 grams per mole, or 6 AMU per atom. And iron has a weight of closer to 56 grams per mole. So how many atoms could fit in there? 1/6 would have 0.16 repeating of a mole of atoms. 1/56 is going to be 0.0178, and then it keeps going, of a mole. So which one has more atoms? Well, clearly the lithium, which weighs less. Now we can do some math with these guys. How many moles of calcium would be in 103 grams of calcium? If I have 103 grams of calcium, how many moles? Well, we need our molar mass of calcium. Calcium, if I do believe, is 40 grams of calcium and 1 mole of calcium. Here's where we can use our unit cancellation. Because I have grams of calcium up top, I need grams of calcium in the bottom, and that would cancel to give us moles of calcium. So 103 divided by 40 gives us, how many moles would that be? 2.575 moles. The equivalent of saying, we have 2.5 dozen. 2.5 dozen. It said 2.5 moles. How many atoms would be in 88 grams of zinc? This one's a little bit harder. I'm going to give myself a little bit more room. If I have 88 grams of zinc, I need to turn this to atoms. The first step is always turn this into moles. So zinc, molar mass, 65 grams per 1 mole. Close enough. Close enough. We'll take it. 65 grams of zinc per 1 mole of zinc. 88 divided by 65 gives us 1.35, we'll say 4 moles of zinc. Now here's where we bring in Avogadro's number. Avogadro's number says 1 mole contains 6.02 times 10 to the 23rd atoms. How many atoms of zinc? I set that up. 1 mole of zinc, atoms of zinc, moles and moles cancel. multiply that by 6.02, you would have how many atoms of zinc? Would have 8.15 times 10 to the 23rd atoms of zinc. A whole heck of a lot. Now that we can turn grams into moles and moles back into grams and all of that to atoms, we need to apply this concept to a balanced chemical equation. Remember that each element must be balanced. So let's look at some simple combustion reactions. So let's start with methane. Methane plus oxygen goes to CO2 and water. Now, you don't have to do this balancing trick each time. I'm doing it just to show that indeed everything is balanced. 1, 1, 4, 2, 2, 3. So carbon is balanced. Hydrogen, I need a 2, which puts that to 4, puts that to 4, and then go back, put that at 2, so that goes to 4. Everything is balanced. So that means 2 molecules of oxygen burn with 1 molecule of methane to make 1 CO2 and 2 waters. So this will tell us how much oxygen are needed, how much CO2 is formed, and how much water is formed. We can now figure out what mass of CO2 would be formed when we burn methane. You can break it down to these 5 steps. Do you have to do the 5 steps every time? Not necessarily. It depends on where we want. But those 5 steps are: 1, balance the equation. Sometimes your equation will already be balanced. 2, determine weight of known. In this case, it's our weight of our methane. That's our starting material. That's usually given by the problem. Find the moles of the known. This case would be the moles of the methane. That's our first real math. Find the moles of the unknown, the desired product. In this case, we're asking what's the moles of CO2. And then step 5 is go the weight of our unknown. Weight of unknown. In this case, it would be the weight of our CO2. We're breaking it down into those 5 steps. We've already done step 1. We balanced it. So step 2, let's say that'd be something I would usually give you. So how much CO2 would be produced if, so CO2, grams of CO2, if we burn, let's say, 75 grams of methane. Step 2, grams of methane is 75 grams. So check. Step 3, moles of methane. To get the moles of methane, we need the molar mass. To get the molar mass, we look up on the periodic table the weight of each molecule, of each atom. So carbon is 12. Each hydrogen is 1. There's 4 hydrogens, so there's 4. The molar mass of methane is 16. So 75 divided by 16 would give us something like 4.6875 moles of methane. So that's step 3. Done. Now, here's where we need our balanced chemical equation. We need to know how many moles of CO2 would be produced. So in our balanced chemical equation, how many CO2s are produced per 1 mole of methane? For every 1 mole of methane, we produce 1 mole of CO2. So how many moles of CO2 would we produce? 4.6875. So we're good. The last step, taking this back to weight. Moles of CO2. The molar mass for every 1 mole of CO2. How many grams of CO2 would you be? Well, carbon is 12. Oxygen is 16. There's 2 of them. That makes 32. 32 plus 12 is 44 grams. So we'd take our 4.6875, we multiply by 44, and we're left with 206.25 grams of CO2. That's our 5th step. That answers our initial question. We've done that. The beauty of this is it doesn't matter what I choose to measure. We can take the same steps if I instead want the number of water. If I say the grams of water, if 75 grams of methane. Well, steps 1, 2, and 3 are the same because the amount of methane is the same. But step 4 and 5 are going to be different. So moles of methane. Well, based on our balanced chemical equation, for every 1 mole of methane, we would produce 2 moles of water. 2 moles of water means 0.6875. When we multiply it by 2, you would get 9.375 moles of water. And the last step, finding the weight of water. So 9.375 moles of water. Water has a different molar weight. So 1 mole of water would weigh how many grams? Well, oxygen is 16. Hydrogen is 1. There's 2 hydrogens. So molar weight of 18 grams. So our number times 18 would give us 168.75 grams of water. With that in mind, we can do this with any aspect of this balanced chemical equation. We can try this again. Go back to our ethanol equation. We just looked at the combustion of ethanol a minute ago. We said C2H6O. Balance that again. 2 CO2. 3 H2O, and I think we said a 3 there. So if I had, let's say, 29 grams of ethanol, of C2H6O, I'm going to ask you 2 questions. 1, how many grams of CO2 would we produce? And how many grams of oxygen would we need? So looking at those, starting, we've already balanced it. So step 1's already done. Step 2, grams of ethanol. We've done that. I've given you that. Step 3 is our first real math again. So 1 mole of ethanol weighs how much? Well, carbon is 12. 12 times 2. Hydrogen is 1. 1 times 6. Oxygen is 16. So 16 plus 24 plus 6 is 46 grams. So 29 divided by 46 is 0.63, we'll say, moles of ethanol. So this number will not change regardless of what I'm looking for. So 0.630 moles of ethanol, 60 I'm going to put 2 steps together. For every 1 mole of ethanol we burn. Now, please note, if this coefficient was anything but 1, we would put that coefficient down there. But since it's 1, it makes it a little bit easier. 2 moles of CO2. And for every 1 mole of CO2, that weighs exactly 44 grams of CO2. Note that moles of ethanol cancel moles of ethanol. Moles of CO2 cancel moles of CO2. So my math becomes 0.630 times 2 times 44. And you get 55.44 grams of CO2 produced. Doing this again with the amount of oxygen needed. 860. Well, for every one mole of C2H6O, we need 3 moles of oxygen from our balanced chemical equation. And 1 mole of oxygen, as we recall, weighs 32 grams because oxygen is 16 times 2. So 0.630 times 3 times 32, because we need to cancel everything out. How much oxygen would we need? We would need 60.48 grams of oxygen. And that is how we do our math for these. Now, that's all well and good for pure elements, but what about elements that are mixed with water? Oftentimes, it's going to be easier to count particles using a volume rather than by weighing them out, which is where we're going to get the term solution. So a solution is a homogeneous mixture of one substance dissolved into another. Homogeneous is from the Greek, homos, genos, which means same, and kind, gender, stock, or race. We're using it to mean mixed uniformly throughout. It's the same all over. So one thing's dissolved into another. Specifically for a solution, we have a solute dissolved into a solvent. The solute is dissolved into the solvent, gets actually dissolved. It is the one that's in smaller proportionality. Sometimes it's really obvious. The solid is almost always the solute when you're mixing into a solution. But if you're mixing 2 liquids, how do you decide which is the solute and which is the solvent? Well, it's the one in greater quantity is the solvent. So the solvent is the substance in greater quantity that actually does the dissolving. So if you mix water and alcohol, you could have a situation where there's more alcohol than water, in which case water ceases to be the solvent. And now suddenly you have alcohol as the solvent. Please keep in mind, to make a solution homogeneous, sometimes stirring is necessary, like in our demo. When I first mix them together, the particles take a while to spread out before it's fully homogeneous. So stirring that and agitating that will help mix those along. Using that, we can measure the concentration, and that's going to be how we're going to count these particles. A concentration is just the expression of the quantity of a solute dissolved into a specific quantity of solution. The quantity of solution is usually stated as the volume. So say like, oh, the concentration is 5 particles per liter. Maybe it's 5 milligrams per liter. Maybe it's 5 moles per liter. It all depends on what we're using to measure that, which the most common way to measure that will be with molarity. Molarity is the concentration term that refers to the moles of solute per liters of solution. So in our demo, when we lower the concentration by 10 of each time, we lowered essentially the molarity by 10. Now, we're going to want the simplest units, and oftentimes we'll use this scale of molarity when we measure things. Let's look at some simple molarity calculations. If I have 1.5 molar sodium chloride. And I used 3 liters. What would be my moles of sodium chloride? What would the moles of sodium chloride be? Well, molarity is defined as a mole over a liter. So to do this, I would have 1.5 moles of sodium chloride over a liter, multiplied by our 3 liters. And the question is, how much would I have? You would have 4.5 moles of sodium chloride. If I dissolved 0.8 moles of hydrochloric acid into 2.2 liters of solution, what would be the molarity? Once again, to get molarity is moles over liters. So to do that, you're going to have 0.8 moles divided by 2.2 liters. And the units are going to be moles over liters, which is equal to molarity. So 0.8 divided by 2.2 is going to be molarity of 0.36 repeating. We can say 364. We didn't really go into significant figures. We're not going to worry about it. And we can finally take molarity all the way to gram. If I had 0.95 molar aluminum chloride and I used 1.5 liters, what would be the mass of aluminum chloride that I deposit? What's the mass of aluminum chloride? So breaking down into 2 steps. One, we're going to take, well, actually 3 steps. One is molarity of known. Step 2 is going to be moles of known. Step 3 would be weight of known. So step 1, what is my molarity? 0.95. To get from 0.95 moles over liters, and then using my volume, 1.5 liters, I would get my moles of known. 0.95 times 1.5. Get 1.425 moles of aluminum chloride. Now this one's the hardest bit. Step 3, what is my weight of known? So for every 1 mole of aluminum chloride, we have to figure out what is the weight of aluminum chloride. Well, aluminum is 27. Chlorine is, we'll say 35.5. That's the one I really don't like to round. And there's 3 of them. So 35.5 times 3 plus 27, it's something like 133.5. So 133.5 times my 1.425, and I would have 190.2 grams delivered. I'd be delivering 190.2 grams of aluminum chloride. Now, molarity is common in science, but it's not so common in everyday life. If you go to the store and you buy something off the shelf, it's not going to give you the molarity of the solution. It's going to give you some sort of a weight percent or volume percent. Commercial goods will show you the active ingredient, and it's usually measured in a percent composition, whether weight by weight or weight by volume, volume by volume. So when you buy vinegar off the shelf, the active ingredient of vinegar is acetic acid. Vinegar is C2H, C2H3O2. Vinegar is that, and that's 5% by mass. So standard store-bought vinegar. If you buy special cleaning vinegar, which it's possible, it's 10% by mass. Hydrogen peroxide, when you buy it from the shelf, is not pure hydrogen peroxide, and thank God it's not. It's 3% by mass. I use sometimes 30% hydrogen peroxide for a violent and explosive elephant toothpaste reaction. If you've ever watched like devil's toothpaste or whatever, some videos online where they use the highest concentration possible with explosive results, you see why you don't want to concentrate it. You want something to disinfect, not corrode your skin. Some things are much higher, like isopropyl alcohol. It's not pure isopropyl alcohol, but it is 70% by weight. Isopropyl alcohol, let's see. So it'd be something like C3, 6, H8, O. C3H8O is the active ingredient of isopropyl alcohol. And of course, bleach. Bleach, you buy bleach at the store. Thank God, once again, it's not so concentrated. It's usually 6% by volume active ingredient, which is sodium hypochlorite, NaClO. So what does that mean concentration-wise? Let's do a couple of these. So if you look at the book, it'll show you how to do vinegar and those guys. I'm going to do vinegar and bleach real quick, just to show you how it's done. Weight percent. So what does that mean? The weight percent means 5 grams out of 100 grams of solution. 5 grams out of 100 grams of solution. Now, a lot of these times we're going to make one big assumption that the solution is 1 gram per 1 milliliter. That the basic density of water is that for every 1 gram of solution, we have 1 milliliter of solution. So that means we have 5 grams of C2, well, HC2H3O2 and per 100 milliliters of solution. With that in mind, you're going to have a couple steps. Step 1, determine percent / setup ratio. 2, turn grams solution to milliliters. 3, turn milliliters to liters. And then 4, turn grams of solute to moles of solute. And that will give you your molarity. If you do those steps. So looking at acetic acid, we have 5. 5 over 100 grams, it gives you 5 over 100 mils. We've already done that step 1. Well, step 1 and step 2. Step 3, there is 1,000 milliliters in 1 liter. And step 4, what is the molar mass of acetic acid? HC2H3O2, 12 times 2 plus 4 hydrogens. There's 3 there and another 1 there. And 2 oxygens, 32. A molar mass of 60 grams of acetic acid per mole. Doing that, so 5 divided by 100, but times 1,000 divided by 60. So 5 times 1,000 divided by 100 divided by 60. A molar mass of 0.833 molarity. Let's try that again with bleach. Bleach is 6 grams of sodium hypochlorite per 100 grams of solution. 100 grams of solution. Well, that is equal to, there's 1 gram and 1 mil. So that takes care of that. And there is 1,000 mils in 1 liter. That takes care of that. Last step is, what is the molar mass of sodium hypochlorite, NaClO? Well, Na is 23. So that chlorine is 35.5. Oxygen is 16. 23 plus 16 plus 35.5. It's something like 74.5. 74.5. So 6 times 1,000 divided by 100 divided by 74.5. Something like 0.805 molar. Not too dissimilar from vinegar. However, if you get vinegar on your clothes, you kind of smell a little funny. If you get bleach on your clothes, you may have ruined your clothes. So there's kind of a little difference on concentration of this versus concentration of that. The active ingredient is still very powerful. Those examples work well in most common concentrations, things we'll see in our everyday life when we go to the shelf and buy things from the store. But how do we deal with trace amounts, trace quantities, like some of the contaminants or pollutants? How do we deal with that dye? That dye would be trace. It was only a drop of this, only a drop of that. How do we deal with something like that where it's almost too small to measure easily? Well, that's when we get into terms like parts per thousand, so parts per million, parts per billion. Essentially, the percent was a parts per hundred. So we can take it one step further. The most common one we'll see is probably ppm, which stands for parts per million. If you want to make it simpler, you could say it's milligrams of a solute per kilograms or liters of solution, because milligram is 1/1000th and a kilogram is 1,000 grams. So 1/1000th over 1,000th gives you 1/1,000,000th. So if you have some that is 35 milligrams per kilogram, it would essentially be 35 ppm. Looking at some examples from the book. In potassium iodide is often mixed into table salt to help prevent the condition called a goiter to form in your thyroid. Your thyroid needs small amounts of iodine to help it function. So they mix something like 7.6 times 10 to the negative 5th grams per gram of salt. If you turn that into parts per million, so you're multiplying that by 10 to the 6th to bring it into place. So they're mixing 76 parts per million of Ki into there. Things like botulism comes from the botulinum toxin that occurs in spoiled food. Well, at least in mice, it can be toxic even up to 50 parts per trillion. So that is very, very toxic. So sometimes this trace concentrations are very, very important, because when we think of water, you think of pure water, you think stream water, you think of deep in the Alps water, you think of rain, you might think of rainwater depending on where you're at. If you're downwind of a tannery or a big factory, maybe not. But you think of like, oh, rain, that's got to be clean water. But even the purest water has dissolved minerals of certain types. Now, the very purest water you can get is actually going to be in a lab where you run it through various columns with cleaning resins to remove all the minerals, or you distill it repeatedly under very carefully controlled conditions so that it doesn't take up any minerals as it goes through the distillation apparatus. Doesn't dissolve any metals. That's the purest water. But in reality, things like rainwater have impurities. Even if it doesn't have minerals, you're going to have nitrogen and oxygen dissolved, some CO2 dissolved in it. These gases will dissolve into it. There's about 0.01 grams of nitrogen dissolved, 0.05 grams of oxygen, and 3.4 grams of CO2 dissolved in 1 liter. All of that is the solubility of that in 1 liter. So when you boil water, or you try to get it to boil, you'll see bubbles appear in the heated tap water just prior to boiling. And that's actually these gases trying to escape. Because one thing about gases is they become less soluble as the temperature goes up. Less soluble as the temperature goes up. So boiling this water is going to make those gases escape easier. Now you'll notice that CO2 has way greater solubility per liter. And that has to do with this reaction that when CO2 dissolves in water, it forms carbonic acid, H2CO3. This is responsible for making most water mildly acidic. This is also the reaction that happens in carbonated waters, carbonated beverages, sparkling waters made by CO2 dissolved in them to make them bubbly, because this will naturally break down again and release CO2 back out. But this makes it slightly acidic. Now, there's plenty of other things that can dissolve into it, like depending whether your auto and industrial pollutants can dissolve into to make acid rain. So like the gases that we talked about being produced by the petroleum. And when this rain falls into lakes and streams, they can sink into the groundwater and contaminate that as well. Most of our drinking water is going to actually come from a groundwater reservoir, with half of all the U.S. getting their water source from a groundwater reservoir, and 3/4 of all cities, of the large cities, getting them that. Because in terms of groundwater, we have more groundwater than all of our lakes, rivers, and streams combined. If you ask Minnesota with its land of 1,000 lakes, so that should tell you there's a lot of groundwater up in there that we utilize. So when we contaminate that, we contaminate everybody's groundwater. Now, all the groundwater will have something in it, whether this could be benign, this could be helpful, but it could be toxic depending on what it is. I mean, water is naturally a good solvent, but it's also mildly acidic because of all that CO2 dissolved, and that mild acidity can really help dissolve some things. So as it's going through the soil, it can pick up various minerals. Now, we can have many natural minerals, like you would see if you bought natural water or mineral water, things like calcium, iron, magnesium, potassium, sodium, fluoride. It all depends on the source. Where are you getting this water from? This stream versus this stream. Some of those minerals are going to help purify it, keep bacteria from forming, and some of them are going to be responsible for the taste. If you try to drink distilled water, which is as purified as we can really get it, you're going to be like, oh, that tastes awful. You need a little bit of the chlorine, a little bit of the sodium, a little bit of those minerals that gives it your flavor. If you get used to your town's drinking water and you go somewhere else and try to drink their water, it's going to be like, oh, that tastes weird. That's because they have different minerals in their groundwater reservoir. And so it's going to taste different to you. Now, as I said, some of these can be harmless. Some of these can even be beneficial. You need some of these minerals in your diet. some of these are going to be good for you. I mean, you need a little bit of potassium, a little bit of iodine, a little bit of fluoride. Fluoride can strengthen your teeth. So you need calcium in your diet. Some of these you're going to take vitamin supplements to try to give more of these, but you can get some of it by just drinking water. But some will also be toxic, even in very low concentrations, depending on what you do. You could have runoff from farms, essentially. Agricultural fertilizer or pesticides can run off and go into the lakes when it rains. You can have industrial waste, whether it's being like a byproduct of like a tannery or something. If they put it into the stream, or it's nearby the stream and it's not properly disposed of, it can run into there and pollute that. There's urban waste, household waste, just your garbage, just a landfill can leak as it rains. It dissolves some of the stuff, crud from the landfill, and then goes into the groundwater if it's not properly contained. So with that in mind, Congress passed the Safe Drinking Act of 1974 that essentially tested for and tried to limit certain common contaminants. That's saying like, oh, arsenic, we're only going to allow 0.05 ppm. Barium, we can limit to 1. Cadmium, 0.01. Lead, 0.05. Sodium, for example, we'll have some sodium in our water, but we say no more than 160. We don't want to give people like hypertension when they drink their water. Now, with such a good idea, we amended it like half a dozen times. Like in 86 and 96, it was amended directly to the bill. In 2005, a new bill was passed that kind of related with this. 2011, 2015, 2016, with Flint, Michigan, and 2018. We have various different things that either make it easier for people to get justice for this, or more testing, or maybe a modification to one thing here or there, but essentially trying to limit this down. Now, this doesn't protect all water. For example, it doesn't protect mineral water. They're exempt because you know you're drinking minerals when you get that. So they could have toxins in it. They probably test it, but they can have a little bit higher if they're mineral. So is carbonated water like seltzer and tonic, because those fall under carbonated beverages and go into the FDA. Sometimes if you have a really small local well that isn't provided to the public, it's not required to follow these regulations. So you'll have to get it personally tested. But if your city pulls from a bigger well, they will have to be tested. Now, there's some issues that aren't just due to carelessness or wanton disregard that we still have to deal with, like carelessness, like, well, I put on a bunch of pesticides right before a big rainstorm, or I physically dumped it into the river. I don't want these batteries anymore. Just chuck it in. But sometimes you just come from society as a whole, like too many cars, too much pollution, and you're going to get this acid rain that's going to contaminate our streams. You get sometimes a gas station goes out of business and they don't empty out the tanks, and that can eventually leak into the groundwater. So all these these set limits, and these are some things we have to deal with. Now, you'll notice some of these limits are higher than others. Part of this has to do with some of these are set because that is literally the limit of detection, at least at the time it was written. We cannot detect any lower. So if I said my measurement only reads 5 ppm or more, or 0.05 ppm or more. So if it's 0.04 ppm and I can't read that number, there's no point of trying to measure for that. So some of them were literally, that was the limit at the time. Some of this, it's just, we cannot purify it anymore. So a little bit of arsenic in that concentrations should not harm you. However, sometimes it's there. You can't really help it. But so too difficult. It's not going to be really good if we have to spend thousands of dollars to purify one drinking glass to get it perfectly safe. Nothing is ever perfectly safe. We just do our best within reasonable costs to make sure you don't die. Make sure you're as safe as we can. Now, this chapter, if you've ever had chemistry in the past, is probably the most similar to what you may have seen in high school. This chapter is a lot of what we will see if you have to eventually take Chemistry 111, which is General Chemistry 1. This is the basic math of chemistry. How do we turn grams into moles? How do we turn moles back into grams? How do we do the stoichiometry? How do we calculate molarity? How do we calculate various concentrations? It's the basics. Now, this is often some of the harder stuff because you have to be systematic. That's the key thing. In all science, you should be systematic of your approach. It means don't just wing it. While sometimes intuition may lead you to the right answer, just like we're supposed to work through the scientific method at all points. We make observation. We use what we know about the world to try to make a hypothesis. And then we go on to try to test said hypothesis. We want to know whether the hypothesis is confirmed or denied. And then we run further tests. If we start skipping steps, we're going to get off on the completely wrong trail. Same way as when we read the problem carefully. We try to determine what we know, what we want to find out, and then we will systematically convert one unit to another. There's a whole range of chemistry all about the analysis and measurement of things to try to tell us how well do we know this result. Is this result accurate? Is this value correct? Are we getting a false positive or a false negative? We want to be able to know this. We want to be able to calculate these things to know, like, oh, can we trust these results? And so this is very important. Now, whether we will fully utilize that, mostly in this chapter. If you eventually take General Chemistry 1, we'll utilize this far more at that time. But for now, there's just a brief dip of the toe in to the science, the math behind the science. Have a good day.